is a FDS, which is not a surface bundle. Example 2. This is also is in the Christopher's paper, and it's due to Alvarez Lopez. Okay, fix lambda irrational number, and phi of lambda is a homomorphism D to Z R mod Z, defined by sending n to the n lambda mod Z. Okay. Then we take a Z cover of Riemann surface, and let M to be the sigma, the product, the twisted product of sigma tilde and R mod Z with respect to this phi lambda. Then this has a Fourier structure as a Fourier given by the image of the sigma tilde times some point in M. And dynamical system is given by the suspension. Okay. In this case, again, the omega, the canonical one form, is given by ds, but the period group has rank 2. So in this case, this is not fiber bundle. Actually, this is an example of the non-compact leaves. The non-compact leaves. And one leaf has a dense in them because the lambda is irrational. This is an interesting example. Our results contain these cases, but still it's not. So I think as Myung-Hyun talked about that, this case actually easiest, simplest case easy because this is an analog of the algebraic curve of a finite field of the surface bundle. This is somehow the analog of maybe regarded as analog of the number ring. It's more complicated. This situation more complicated. So the procedure definition is due to copy. And suppose each leaf has a complex holomorphic structure. For these two cases, actually, the sigma is an orientable surface, so it has a complex structures. This example satisfy this assumption. And suppose F as then the smooth map M to P1 is called FDS meromorphic. Copy call the F smooth map F is FDS meromorphic if F restricted to the each leaves is meromorphic in the usual sense, and zeros and poles of F lie along the finitely many orbits, closed orbits. Okay. Okay. So So now it's finish the preparation of the notion. So now let's go to the section 2. Section 2 is a foliated, smooth Drinic homology. Okay. So now let S be a three-dimensional FDS. Okay, and suppose X is some manifold of M. Take any some manifold M, and the definition. We introduce first foliated smooth Drinic complex for natural number n. The foliated smooth Drinic complex is defined by the following truncated drum complex, denoted by CS of n. The first term is a period group times 2 pi I to the power of n. Lambda is a period group, then which inject in the smooth sheaf of smooth function, and we have here the drum complex to the n-1 form. Here the AI is the sheaf of a smooth I form on X. On X. Then this is a definition of the foliated smooth Drinic complex, and then we replace just this initial term from usually this is a Z. We replaced it by the period group. The foliated Drinic homology is defined by the hypercohomology of this complex. Let me write just simply H of hypercohomology of this complex. So maybe this is a definition. Maybe this may be written as H dot green and X and lambda S of n. This is our definition of the foliated Drinic homology. For example, for example, if period group is Z, this is the case of the fiber bundle over circle, then in this case it's just our foliated Drinic homology is nothing but the usual Drinic homology, Zn. Usual smooth Drinic homology. This is usual smooth Drinic homology. Studied by Brzezinski. So for example, the H1 of D of Z1 is this. This is just invertible complex valued invertible function this is a smooth invertible functions on X. Here the invertible means that this means that this is a C star value, C star valued function. But C star is just the C mod of the Z of 1. Okay, so our Fourier-Dirichlet cohomology of H1 of X of the C S1 is the space of a smooth C mod lambda S 1 valued functions on X. This is a feeling of this the cohomology group. Okay, this is somehow the strange function. It's an odd function, but this we will introduce this one. And for example, it's if F is FDS meromorphic in the sense of copy, then the cohomology class represented by the check cocycle log of F restricted to U alpha minus log F restricted to U beta, and the log F restricted to U alpha beta, U alpha and intersect U beta. Here is a U alpha is just an open cover. This is open cover of X. So then if F is for it FDS meromorphic, then this check cocycle gives cohomology class of our Fourier-Dirichlet cohomology, Fourier smooth Dirichlet cohomology. Okay, and the next one is important. Next remark is important. If a fixed base point in X, and we consider the following function attached to the canonical one form, X to the C mod lambda S1 is given by sending X to the integral of taking some path from B to X of omega S. This is a well-defined function, and this gives some classes of this cohomology class. H1 Fourier smooth Dirichlet cohomology, because the ambiguity depending on the choice of path is absorbed in this pure group. So we have this cohomology class, and we call this is a canonical class. This is we call the canonical class of FDS. Okay. Now we need to develop the integration theory of this Fourier smooth Dirichlet cocycle. To define the holonomy. Okay, so the section 3 is integration theory. Of the Fourier smooth Dirichlet cocycle. This is due to the Gomi Terashima. In their paper, let me give a reference. Their paper is appeared in International Mathematical Research Notices 13 in 2000, and Mathematical Research Notices number 8 in 2001. Okay. would like to define for smooth, foliated smooth Doreen cohomology class and n-1 dimensional submanifold y of x. Would like to define integral of Doreen cocycle over y. Okay. Definition is given as follows. This is very technical thing, but this point was, in some sense, obscure in the work of Brzezinski, but Gomi Terashima made it clear by the following definition. The first, we choose an open cover of x. Okay. Next, we choose a check cocycle say m alpha 0 to alpha n. This is a index of open cover, and the theta 0 is zero form, alpha 0 to alpha n minus 1 to theta 0 to theta n minus 1 of alpha 0. This is zero form representing C. We use a check cocycle, a check description of this cohomology, and we choose. Next, we choose a triangulation K of y, which is sufficiently fine, such that the sigma, the simplex sigma is contained U of phi sigma. Sufficiently fine, so that there exists a map phi from the triangulation to the index I. I is the index of open cover, index I, such that each simplex is contained U of phi of sigma for any simplex of the triangulation. Then the definition, the integral y of sigma is defined to be the sum over I equals 0 to n minus 1, or sum of this is a flag of simplex in K, and the integral of sigma n minus 1, integral over the simplex of this form, differential form, phi of sigma n minus 1, sigma n minus 1 minus I, and we take a mod lambda s of n. Okay? This definition is complicated, so please refer to these papers. It doesn't matter. We can well define some integration of Doreen cocycle over some submanifold. Then the important theorem for us is the following Stokes theorem. Proved by Gomi Terashima. Theorem first, this is due to Gomi Terashima, is a Stokes type theorem. Suppose y is the boundary of the n-dimensional manifold of Z. Okay? Then the integral over C is the integral over Z of omega of C mod lambda S of n. Whereas the omega C is a curvature, this is n curvature of the Torini cocycle, which is defined by defined by the image of C, and the natural map of the Fourier smooth Torini cohomology to the n form on X induced by the morphism of the complex of CS, and this is a complex of lambda Sn to 0 to a to the n minus 1. And here is a morphism complex. From here we have the differential of an, and the image of this cocycle, and this morphism. Okay. Then we have just Stokes theorem. So now, our final section. Section 4, the less velocity law. Okay, so let S be a three-dimensional. This is a three-dimensional FDS with each leaf so having a complex holomorphic structure, the Riemann surface. Then suppose we have Fg is FDS monomic function in the sense of copy. Monomic function, and 0 and poles lie along closed orbit, some finitely many closed orbit. Okay. Then we define Z to be the complement we would like to define that first local symbol, tame symbol in this situation. So we define the Z to be the complement of M of the union of the tube neighborhood of gamma I. Okay, so the boundary of Z is just the union of tori, disjoint union of tori, which is the boundary of tube neighborhood of gamma I. Each gamma I is a not in the M. Okay, then we define for any gamma is a closed orbit. We define the local symbol, the analog of Hilbert symbol, or the tame symbol, by denoted to f of g at gamma is the integral over the boundary of tube neighborhood of gamma of the Torini cocycle Cf, Cg, C omega s. Mod, we take a mod lambda s, the 3. Okay, this cocycle is belonging to the H3 of Z of CS3. So this integral is defined by that in the previous section. Then our theorem is that our theorem, the reciprocity law, is if you take all closed orbit and the sum of all this local symbol is 0 mod lambda s of n lambda s of 3. As we saw that the proof is easy. Proof is just this follows from the Stokes theorem because this sum is nothing but by definition of this sum is just the integral over the boundary over z. This is v of the c of f and c of g and c of omega s. Okay. But using the Stokes theorem, the theorem 1, let this denoted by c, then this is a z of the curvature of c, but we assume that each leaf has a harmonic structure, and if you write down that this differential form in the locally, this should be 0. So this is 0. That's the end story. Yes, I finished.
Questions? So it seems like all the pieces of your computation are available for a three-manifold with a contact structure where the read vector, the read flow, then plays the role of your dynamical system. But then this wouldn't be 0, would it? There would be some invariant of the contact structure?
Yes, maybe. Yes, the interesting question is to give some sufficient condition to that curvature to be 0. But we assume the holomorphic. I think that's natural in our situation. So each leaf has a Riemann surface. Yeah, but it's sorry, I'm not familiar with contact geometry.
Yes. Do you expect some relation with enhanced Chern-Simons theory? Enhanced Chern-Simons theory.
Enhanced?
This thing
I'm sorry, I don't know.
the physicists are doing with extra circle action.
Sorry, I don't know much. I don't know about the physics.
I'll ask later.
Sorry.
Thank you.
Any other questions?
Refine. The word is refine. Refine Chern-Simons.
Refine.